everyone, and welcome. Today, we are going to tackle one of the most powerful tools in all of science. Yep, the periodic table. Now, I know, it can look a little intimidating, right? But I promise you, by the end of this, you're not going to see it as some crazy list to memorize. You're going to see it for what it really is, a map, a logical guide that you can actually read and understand. So, you ready? Let's get started.
So, does looking at the periodic table ever make you feel like you're just facing this huge random collection of elements that you have to somehow cram into your brain for a test? You've got metals, nonmetals, gases, solids. It seems like they all have their own rules. If you've ever felt totally overwhelmed by it all, trust me, you are definitely not alone.
But here's the secret, okay? What if I told you this chart is actually the ultimate cheat sheet? Yeah, for real. It's a code book that, once you learn how to read it, lets you predict how elements are going to behave and why they do what they do. And today, we are going to crack that code together.
So here's our game plan. First, we'll crack the code of the table's basic layout. Then, we'll meet the most important element families and uncover the real secret behind why their properties repeat. After that, we'll decode all the major trends using a really simple analogy. And finally, I'll wrap it all up with a killer revision guide. Let's do this.
All right, Section 1, Cracking the Periodic Code. Now, we've probably all heard of Dmitri Mendeleev. Total genius, right? He first arranged the elements by atomic mass and even left gaps for ones that hadn't been discovered yet. But the modern table we use today, that's all thanks to Henry Moseley, who made one critical discovery that honestly changed everything. This right here, this is the golden rule of the modern periodic table. What Moseley figured out was that an element's true identity, the thing that controls all its properties, isn't its weight, but its atomic number. And what's that? It's just the number of protons in its nucleus. That's it. This simple, elegant change from atomic mass to atomic number fixed all the little kinks in the old tables and gave us the perfect, predictable system we have today. So if you remember one thing, remember this. It is all about the protons.
Okay, so let's jump into Section 2, Meet the Element Families. Now that we know the organizing rule, let's explore the table's geography. We're going to look at its two main parts, groups and periods.
So, the vertical columns, the ones that go up and down, those are called groups. The easiest way to think about them is as families. Just like in a real family, all the elements in the same group share similar characteristics and behave in similar ways chemically. The horizontal rows, the ones going side to side, are called periods. Think of these like the floors of a building. Each new period, each new floor down, means a new energy level, or what we call an electron shell, is being added to the atom.
Now, you don't need to memorize all 18 groups, but let's meet the rock stars, the ones you absolutely have to know. All the way on the far left in Group 1, you've got the super reactive alkali metals. Right next door in Group 2 are their slightly calmer cousins, the alkaline earth metals. Then if we jump way over to the right in Group 17, we have the halogens. These guys love to form salts. And in that final column, Group 18, we've got the noble gases, kind of the cool, unreactive loners of the table. And that big block smack in the middle, that's home to the transition elements.
Now for the periods, and you're going to love this, the rule here is wonderfully simple. The period number equals the number of electron shells an atom has. That's it. An element in period 2, like carbon, it has 2 electron shells. An element way down in period 4, like iron, yep, it has 4 shells. This simple one-to-one connection is the absolute key to understanding everything that comes next.
Which brings us to the big question in Section 3, the secret of periodicity. Why do these properties repeat? Why are all the elements in Group 1 so similar? Get ready, because this is the real aha moment of the whole topic.
And there it is. The secret is that properties repeat because the pattern of the outermost electrons repeats. That's the whole reason. All the elements in a single group act like a family because they all have the exact same number of electrons in their outermost shell. We call those valence electrons. The halogens, they all have 7 valence electrons. The alkali metals, they all have 1. That's it. That simple repeating pattern is the engine that drives every single trend in the entire periodic table.
Okay, now that we know why the properties repeat, let's look at how they change as we move around the table. Welcome to Section 4, Decoding Periodic Trends. And here's the best part. Every single trend we talk about can be explained by a simple battle between two competing forces.
Think of it like a constant tug-of-war happening inside every single atom. On one side, you have Captain Nucleus. This is the nuclear charge, the positive pull from the center of the atom. As you add more protons, this pull gets stronger, yanking the negative electrons in tighter. On the other side, you've got the shielding shells. Every time you add a new shell of electrons, it acts like a shield, pushing the outermost electrons further away and making it harder for the nucleus to hold on to them. So every trend we're about to discuss just comes down to one question. In this tug of war, who wins?
All right, it is time for our trend showdown in Section 5. And first up is the most fundamental trend of them all, atomic size, or what we call atomic radius.
So what happens as we go down a group? Well, the atom gets bigger. Why? Because with each step down, we add a whole new electron shell. In this direction, the shielding shells win, no contest. More shells mean a bigger atom. Simple. But now look at what happens when we go across a period from left to right. The size actually decreases. Now that seems weird, right? We're adding more stuff, more protons and electrons, shouldn't it get bigger? But in this fight, Captain Nucleus wins. We're staying in the same shell, but we're adding more and more protons to the nucleus, beefing up its positive charge. That stronger pull just sucks the entire electron shell in tighter, making the atom smaller.
Next trend up, metallic character. At its core, being a metal is all about the tendency to lose electrons. The easier it is for an atom to give away its outer electron, the more metallic we say it is. So let's just think logically for a second. Which atom do you think would lose an electron more easily? A tiny one where Captain Nucleus has a super tight grip, or a big one where that outer electron is super far away and shielded by other shells? The big one, of course. This means metallic character is directly tied to atomic size. And the trend follows that logic perfectly. As we go down a group, the atoms get bigger, making it easier to lose that outer electron. So metallic character also increases as we go down a group. But as we go across a period, the atoms get smaller. The nucleus holds on way tighter, making it much harder to lose an electron. So metallic character decreases across a period. See? No memorization, just pure logic.
Okay, now let's talk about ionization potential, which is sometimes called ionization energy. Think of this as the price you have to pay, in energy, to snatch an electron away from an atom. If an atom holds its electrons really tightly, the price is going to be super high. If it holds them loosely, the price is low. So this is basically the exact opposite of metallic character. And the trend shows exactly that. As we go down a group, the atoms get bigger and that outer electron is further away, so it's way easier to remove. The price, the ionization energy, decreases. But as we move across a period, the atoms get smaller and Captain Nucleus's grip gets stronger. It is much harder to steal an electron, so the price to do so increases. See? It all comes back to our tug of war.
Okay, let's flip the script. Instead of removing an electron, what about adding one? This is called electron affinity. It measures an atom's desire for an extra electron. When an atom that really wants an electron gets one, it releases energy as a little celebration. The more energy it releases, the higher its affinity. So which atoms have the highest desire? Well, the small ones, where an incoming electron can get really close to that strong positive nucleus.
And our final trend is electronegativity. This one is very similar, but it's specifically about an atom's pulling power on electrons when it's already sharing them in a chemical bond. Think of it like that tug of war again, but this time between two different atoms. The most electronegative element, fluorine, is the undisputed champion of this game. It pulls shared electrons towards itself more powerfully than any other element. And just like with electron affinity, this power is strongest in small atoms with a very strong nuclear charge.
All right, we've made it to Section 6, your ultimate revision guide. We have cracked the code, we've met the families, we've learned the secret, and we've battled it out with all the trends. Now let's put it all together into one simple, super powerful revision tool.
This right here, this is the whole shebang. Seriously, this is your key to acing this chapter. I want you to pause right now and grab a screenshot of this slide. It summarizes every single trend we just discussed. And notice how everything, and I mean everything, connects back to atomic size. It's all determined by that fundamental battle between the pull of the nucleus and the shielding of the electron shells. If you can master that one concept, you can honestly figure out all the others.
So there you have it. The periodic table isn't some random list to be memorized. It's a beautiful, logical system just waiting to be understood. Once you master the core ideas, atomic number, electron shells, and that constant battle between nuclear pull and shielding, you can predict almost anything about an element just by finding its address on the map. So now that you're a pro, what's your best trick or mnemonic for remembering the trends? Share it in the comments below. Let's help each other out. Thanks for watching.